Geometrical representation of linear polynomials. Welcome, everyone. Today, we are moving from the purely algebraic side of polynomials into the world of geometry. To start our introduction, let's quickly recap what we learned in our previous lesson. We established that the zero of a polynomial, which we can call p of x, is simply a specific value, let's call it k, that makes the entire polynomial equal to 0. In other words, when you plug k into the equation, p of k equals 0. Now, today we are going to take that concept and visualize it. When we take a polynomial and represent it on a coordinate plane, we are essentially treating it as a function, where y equals p of x. This allows us to see the polynomial not just as a set of numbers, but as a shape or a path on a graph. As we progress through today's lesson, you will see that for a linear polynomial, the connection between the algebraic zero we calculate and its actual physical position on the graph is incredibly straightforward and consistent. By the end of this session, you'll be able to look at a straight line on a graph and immediately identify its zero just by looking at where it crosses the horizontal axis. Understanding the linear polynomial. Now that we've introduced the concept of a zero of a polynomial, let's take a closer look at the specific type of polynomial we are focusing on today, the linear polynomial. First, what makes a polynomial linear? In mathematics, we define this by its degree. A linear polynomial is simply a polynomial of degree 1. This means the highest power of our variable, $x, is exactly 1. To work with these in a more structured way, we use a general form. We can express any linear polynomial as p$ of x$ equals $1 times x$ plus b$. In this equation, $1 and b$ represent any real numbers. However, there is one very important condition to remember. $1 cannot be equal to 0. If $1 were 0, the x$ term would disappear, and we would no longer have a linear relationship, but rather a constant one. Keep this in mind, because as we move to the next slide, you'll see how this specific structure is what creates the straight line shape on a graph. The nature of the graph. When we plot the equation, y equals x plus b, on a Cartesian plane, the resulting graph is always a straight line. This is a very important characteristic to remember. The reason for this is quite simple. This equation is a first-degree equation in two variables, which geometrically represents a linear relationship. Because the power of our variable x is just 1, the rate of change remains constant, ensuring that the path between any 2 points on the graph never curves, but stays perfectly straight. This straight-line nature is exactly what allows us to use the intersection with the x-axis to find our zero, which we will explore in the next slide. Now that we have defined what a linear polynomial looks like algebraically, let's look at what happens when we move from the page to the coordinate plane. Finding the zero geometrically. Think back to our first slide, where we defined a zero as the value that makes the polynomial equal to 0. When we move from an equation to a graph, we treat the polynomial as a function, which we call y equals p of x. So, finding the zero is essentially asking, at what point does the value of y become 0? If you look at a Cartesian plane, where does the value of y equal 0? It happens exactly when we are sitting right on the x-axis. Because of this, there is a beautiful connection here. The zero of our linear polynomial is simply the x-coordinate of the specific point where our straight line crosses or intersects the x-axis. Now, if you don't have a graph in front of you and you need to find this point using just the equation, you can follow these 3 simple algebraic steps. First, take your equation, y equals x plus b, and set y to 0. This gives us 0 equals x plus b. Second, our goal is to get x by itself. So, we isolate the term containing x by subtracting b from both sides. This leaves us with a x equals negative b. Third, to solve for x, we divide both sides by a. This results in x equals negative b over a. So, to wrap this up, we can conclude that the straight line will always intersect the x-axis at the specific coordinate point, negative b over a 0. Keep this formula in mind, because in the next slide, we are going to see how this works in a real-world scenario involving a prepaid gift card. Now that we understand that a linear polynomial takes the general form of a x plus b, let's bridge the gap between algebra and geometry. Real-world application example. Now that we understand the theory behind linear polynomials and how they form straight lines, let's move from the abstract algebra to a real-world application to see how this actually works in practice. Imagine you have a prepaid gift card with an initial balance of $20. Every time you decide to buy a specific snack, you spend $5. We can use this scenario to create a mathematical model. If we let x represent the number of snacks you have purchased, we can represent your remaining balance, which we'll call y, as a linear polynomial. Looking at our polynomial here, we have p of x equals 20 minus 5x. Let's break this down step by step using the analysis tools we discussed in the previous slides. First, let's identify our coefficients. Comparing this to our general form, x plus b, we can see that a equals -5 and b equals 20. Next, let's consider the geometric meaning. If we were to plot the equation y equals 20 minus 5x on a coordinate plane, we would see a straight line. This line starts at 20 on the y-axis, representing your starting balance, and because our value is negative, the line slopes downwards as x increases. Now, here is the most important part, finding the zero. In this context, the zero of our polynomial represents the exact number of snacks you can buy before your balance hits $0. To find this value, we perform a simple calculation. We set y to 0, which gives us the equation 0 equals 20 minus 5x. To solve for x, we first move the 5x term to the left side, resulting in 5x equals 20. Dividing both sides by 5, we find that x equals 4. So, what is our conclusion? The graph of this equation intersects the x-axis at the point 4, 0. Geometrically, this tells us that after purchasing exactly 4 snacks, your balance becomes 0. In the next slide, we will look at a more formal mathematical example to practice the plotting process itself. Step-by-step mathematical example. Now that we have seen how the concept works with a real-world example of a gift card, let's move into a more formal mathematical demonstration. On this slide, we are going to work through a concrete example step-by-step to plot a polynomial and find its zero manually. Let's take the linear polynomial p of x equals 2x plus 4. Our goal is to plot this on a graph and identify its zero. In step 1, we need to create a table of values. Remember, since we are dealing with a straight line, we don't need a long list of numbers. We only need at least 2 points to define the line. Let's pick 2 easy values for x first. If we let x equal 0, then y equals 2 times 0 plus 4, which simplifies to y equals 4. This gives us our first point, 0, 4. Next, let's try x equals -2. When we plug that in, y equals 2 times -2 plus 4, which is -4 plus 4, resulting in y equals 0. This gives us our second point, -2, 0. Moving to step 2, the next task is to plot these points. You would take your coordinate plane, mark the point 0, 4 on the y-axis, and the point -2, 0 on the x-axis, and then use a ruler to draw a straight line passing through both. In step 3, we look at the graph to identify the x-intercept. If you look closely at where your line crosses the horizontal x-axis, you will see it intersects exactly at the point -2, 0. Finally, in step 4, we perform a verification. We want to make sure our visual observation matches our algebraic calculation. Using the formula we discussed earlier, where x equals -b over a, we identify our coefficients. Here, a equals 2 and b equals 4. Plugging these into the formula, we get x equals -4 divided by 2, which equals -2. As you can see, the algebraic zero we calculated and the geometrical intersection point we found on the graph are identical. This confirms that our method is consistent. Key takeaways. First, remember that whenever you see a linear polynomial, which we write as p of x equals a x plus b, the graph will never be curved or wavy. It is always, without fail, a straight line. Second, because it is a straight line that isn't horizontal, a linear polynomial will have exactly one real zero. There won't be 2 or 3 different answers, just one unique value. Third, we need to connect the algebra to the geometry. When we talk about the zero of the polynomial, we are looking for the x-coordinate of the specific point where our straight line crosses or intersects the x-axis. Finally, if you want to find that point without even looking at a graph, you can use the formula we derived earlier. The coordinates of this intersection point will always be negative b over a, followed by a 0. All right, let's bring everything we have discussed today together. As we reach the end of this lesson, I want you to focus on these key takeaways, as they form the foundation for everything we will study in coordinate geometry. Keep these points in mind, because in our next slide, I am going to highlight some common pitfalls where students often lose marks during exams. Common mistakes to avoid. Now, before we conclude our lesson, I want to highlight a few common pitfalls that students often encounter when working with the geometric representation of linear polynomials. Paying attention to these will help you avoid unnecessary errors in your exams. First, be very careful not to confuse the x-intercept with the y-intercept. It is a very common mistake to look at the point where the line crosses the vertical y-axis, which, as we discussed earlier, is simply the value of b, and call that the zero. Always remember, the zero of the polynomial refers specifically to the value of x that makes the output 0. Therefore, the 0 is always found where the graph intersects the horizontal x-axis. Second, watch out for sign errors during your algebraic calculations. When you are using the formula x equals negative b over a, the signs can get tricky. If your b value is already a negative number, remember that negative b becomes positive. For instance, if you are given the polynomial p of x equals 2x minus 6, when you calculate negative 6 over 2, it simplifies to 6 over 2, giving you a 0 of 3. A small slip with a minus sign can lead you to the wrong side of the graph. Finally, never forget the essential condition that a cannot be equal to 0. If the coefficient were to become 0, the x term disappears, and you are left with p of x equals b. This is no longer a linear polynomial. It is a constant polynomial. Geometrically, this results in a horizontal line that stays at a fixed height on the y-axis, and depending on the value of b, might never intersect the x-axis at all. Keep these points in mind, and you will have a much more accurate understanding of how these algebraic equations translate into geometric lines.